All right, this is Precalculus. We are on page 278, 4.4, but before we start rational functions, do not forget, right, to smash like, subscribe, and turn on notifications. All right? Now, let's talk about polynomial functions. What's a polynomial function? What's the definition? Y'all look at me.
Multiple degrees, multiple terms.
Multiple degrees, multiple terms. What can it not have?
Variables under the radical or under the denominator.
No variable under a radical, no variable in the denominator.
No negative exponents.
No negative exponents, because that means it goes to the denominator, right? What is the domain of a polynomial function?
All reals.
All reals.
All reals.
Except for
No.
mine. Yeah, just all reals.
Yes. What about the range?
No negatives? Oh, wait, no. That's just for exponents.
If it's an odd degree, the range is going to be all reals. Because remember, odds are going to start in quadrant 3, end in quadrant 1. It's going to be all reals. However, if it's an even one, it's either going to open up or open down, right? So your range is going to be from one of those, the smallest minimum point, to positive infinity, or negative infinity to the highest max point. You remember the maxes and the mins?
Yeah.
Do you remember multiplicity?
Yeah.
What does multiplicity tell me?
The degrees. Does it?
The multiplicity is the degree of a term, yes. But what does it tell me? What does multiplicity tell me?
How many times a particular number?
If it's even or odd, remember, if it's even, it tells me, if the multiplicity
Yeah,
is
exactly.
even, it what?
It touches it.
Touches and returns,
Oh, yes.
right? If it's odd,
It
it crosses. Got it? All right. And polynomial functions are continuous, right? Polynomial functions are continuous. There's no breaks, no jumps, no holes in the graph. Got it? Well, now we're dealing with rational functions. So we're going to be on the right-hand side of this form, of this little handout, all right? A rational function is the quotient of two polynomials. So you have a polynomial in the numerator over a polynomial in the denominator. And we are going to have breaks in these graphs. So there are going to be places where, because we have a polynomial in the denominator, wherever that denominator equals 0, you're going to have a hole or a jump or a break in the graph. So they're going to be discontinuous at some point, because we are now going to have x's in the denominator. All right? And those breaks are going to be one of two things. They're either going to be holes or they're going to be asymptotes. We're going to cover that today. All right, holes or asymptotes. All right, look at the bottom of page 278. You see examples of rational functions. You see them? 1 over x. Where would that not be defined? When x is equal to what? 0. The next one, 4x minus 3 over 2x plus 1. Where would that be undefined?
X is 0.5.
Negative 0.5, yeah. All right, and then the next one you'd have to factor and then look at what the zeros are. So it's zeros of the denominator that make it discontinuous. Make sense? Got it?
No, ma'am, I still don't understand.
Okay. For a rational function, it will be discontinuous where the denominator equals 0, because that's where it's undefined. We can't take a number divided by 0. So if it's 1 over x minus 1, we're going to have a whole or an asymptote at where that denominator, the value of x, where the denominator equals 0. Got it? Make sense? All right. All right, so how can we know the domain? Well, now we have a rational function. So the domain is all reals with 2 exceptions. What are those 2 exceptions? Huh? The domain for a rational function is going to be all reals, except, what are the 2 exceptions for domain?
The denominator.
That's right. Yeah. So it's going to be all reals, except the denominator cannot equal 0.
And under the radical cannot equal a negative.
Whatever's under the radical has to be greater than or equal to 0. But if that radical's in the denominator, it has to be greater than 0. For a rational function, it's just going to be a polynomial divided by a polynomial. So really, we're going to look at this piece for our domain. We're going to look at where the denominator equals 0. Got it?
Mm-hmm.
All right. So look at example 1. Example 1 has this function. F of x is 1 over x squared. What is the domain? The domain is all reals except x cannot equal 0. So you could write it in interval notation, negative infinity up to 0 and 0 up to positive infinity, or you could write it the other way. Make sense?
Yep.
Same domain rule that we have been using. I have a nice dark green in here somewhere. All right. B is slightly harder to figure out. B is g of x equals x squared plus 3x plus 1 over x squared minus x minus 6. But still, we're just looking at the denominator. So you want to factor that denominator. And what would that denominator, when we're talking about domain, for rational functions, we're only going to look at the denominator, right? So we want to factor the denominator. What is that denominator factored?
X minus 3x plus
X, say that again, minus 3.
x plus 2.
Okay, so what can x not be equal to?
3 or negative.
So it's all reals, right? Except x cannot be equal to 3 or negative 2. So that would be your domain.
Why can't it? Oh, because they're.
3 would make that
it
0.
Yeah.
And 0 times anything is 0. Yes?
So these questions, they're just asking for what the
Domain.
is. Okay.
Because now we're in rational functions.
So you would write what it cannot equal and then everything.
All reals except what it cannot equal. Yes. Make sense? Okay. Now, we're going to talk about intercepts. There's 2 intercepts. There's x-intercepts and there's y-intercepts for rational functions. All right, for the x-intercepts, you're going to look at the zeros of the numerator. Only. Because 0 divided by a number equals 0. And remember, the x-intercepts is when the value of y is 0, right? We're going to look at an example in just a minute, all right? And I believe that I have, look at the numerator for your intercepts, your x-intercepts. I should have put x-intercepts. Your y-intercept is going to be when x equals 0, right? So looking back at this one, it's just your constant in the numerator over the constant in your denominator. Because when x is 0, that's 0 plus 0 plus 1. And that's 0 plus 0 minus 6. So your y-intercept is just your constant over your constant. Whatever the constant is. So it's the constant number that's in the numerator over the constant number that's in the denominator. Make sense?
So it'd be negative.
Negative 1/6 would be this y-intercept. All right, so we're going to answer those questions for example 2. All right? Now, here's one thing you have to remember, okay? It's only an x-intercept if it is a 0 of the numerator and not a 0 of the denominator. So it's a 0 of the numerator and not a 0 of the denominator.
What exactly does that mean? So
Okay, so somebody explain what this means. A 0 of the numerator that's not a 0 of the denominator.
So,
Okay, I'm going to write an example. What is the zeros of the numerator?
negative 1 and 2.
Numerator.
Negative 1.
Negative.
Denominator.
Negative 1, yes.
So it can't be negative.
So it can't, that's not an x-intercept.
Oh, because then I would just equal something.
It doesn't equal 0. It equals undefined.
If it's over.
Got it? Now, if I change that, right, then we have a 0 of the numerator of 1. That's not a 0 of the denominator. That's an x-intercept.
Oh, okay. So,
Got it? Got it?
Wait.
Okay. This x-intercept would be 1 because that is not a 0 in the
So
denominator.
since it's the denominator, denominator is -1 and 2, it
Correct.
It doesn't cancel out because the
Because
one of those
opposite
opposites.
signs.
So basically, something in the numerator cannot be the same as something in the denominator?
Correct, because I'm going to tell you something about that in a minute. Okay? That's going to be an indicator that there's a hole in the graph.
Okay.
Okay? All right. So now let's look at example 2. Are we ready? Are we ready? Ready? Okay. Example 2. X squared minus x minus 2 over x minus 1. All right. Now, what is the y-intercept? Negative 2 over negative 1, which is 2. So that would be 0, 2. Got it? Negative 2 over negative 1. It's constant over constant. Okay? Now, what is the x-intercept? Maybe plural. Okay, can we factor this?
-1, -2.
All right, so what are the factors?
-1,
Can't be both negative.
-2. Oh, right. -2.
-2, +1.
So it's 2 and
so
negative
it's
1.
negative.
So it's 2 and -1. It's those because that's not also a 0 of the denominator.
Wait, hold up. But
I'm gonna wait.
yeah, in the numerator, you change the +1 to a negative, and in the denominator, that 1 is also a negative. So, is it like
For the y-intercept? Or for the x-intercept?
I think for the x?
Okay, for the x-intercept, you look at the zeros of the numerator. We factored this.
Yeah, I know that. But I'm saying like it's positive to a negative 1, right? But
Correct.
But there's also a negative 1 in the denominator. So shouldn't that like?
No. The 0 of the denominator would be positive 1 because it's whatever makes it 0. So at positive 1, there is something we're going to talk about in a minute.
That's what I was talking. That's what I was talking about. You change that to a positive 1.
No, we don't change anything to a positive 1. Okay, listen. Here's the rule. Y-intercept, constant in the numerator over constant in the denominator. X-intercepts are zeros of the numerator that are not zeros of the denominator. Got it? That's where it's going to cross the x-axis. All right? All right. So, we've talked about domain, and we've talked about x and y intercepts. Got it? Now I want to talk about asymptotes and holes. So it's on this side. It's right here. So I want to talk about holes first, all right? And then we're going to go over the examples, all right? When is there a hole in the graph? Polynomial functions don't have holes in the graph. Only rational functions, which is a polynomial divided by a polynomial. They have holes in the graph. Your calculator doesn't show a hole in the graph. It looks like a continuous line. You can't graph a function and say, oh, there's a hole here. You can't do that, all right? But if you just read with me, look, there's holes in the function where there's a 0 of the denominator and a 0 of the numerator, except where the multiplicity of the factor is higher in the denominator than in the numerator. Okay, so I'm about to show you. All right. All right. There's a hole in the graph. There's a hole at x equals 1. Why? Because that's a 0 of the numerator and the denominator, and their multiplicity is the same. They're both raised to the first power.
So holes only apply when they and x and y have the same.
This is not x and y.
I mean, no, there's
This
x
is
in the denominator.
zeros.
Yeah.
This is zeros. Of the numerator are the same zeros of the denominator. And they have the same multiplicity. They have the exact same multiplicity. Got it? Okay, are you ready? That's a hole. I said there's an exception. All right, now, how is this different from this? The multiplicity is greater in the denominator than it is in the numerator. That's the exception. Except where the multiplicity of the factor in the denominator is higher than it is in the numerator.
What if the numerator's multiplicity is
Okay.
higher?
Then there's going to be an asymptote, okay? So, if this is the case, there's a vertical asymptote at x equals 1. When the multiplicity is greater in the denominator than it is in the numerator, this is what happens. At x equals 1, there's this vertical asymptote, such that there's something on the left-hand side of this graph, and then there's something on the right-hand side of that asymptote. but the graph does not cross that vertical asymptote. Okay? So literally, so hole in the graph, when a term can be completely canceled. Hole in the graph, when there's a factor that can be completely canceled. When you have this, you would have this. The term cannot be completely canceled. When the term cannot be completely canceled out of the denominator, then that's an indication of vertical asymptote. Got it? So, hole in the graph when all your terms can be canceled. Numerator and denominator. Got it? Hole in the graph. There's a vertical asymptote. Look at this on your little sheet. Where there's a 0 of the denominator that is not a 0 of the numerator. So because we can cancel these out, this becomes a vertical asymptote. So for this example, we have 2 vertical asymptotes. So we have vertical asymptote at zeros of the denominator that are not zeros of the numerator. In other words, you can cancel them out, right? Does that make sense? Does that make sense? So holes and vertical asymptotes have to do with zeros. Right? Holes and vertical asymptotes have to do with zeros. They're holes in a graph when I can cancel every one of those terms that are in the numerator with one in the denominator. Does it make sense? Mm-hmm. There's a vertical asymptote of whatever zeros are in the denominator after I do all the canceling. And we're going to walk through this and practice this, okay? Horizontal asymptote. So a vertical asymptote is never crossed. A vertical asymptote, something happens, and as the graph approaches that vertical asymptote, it either goes to positive or negative infinity. That's what the graph is going to do. From the left, this is from the left, and from the right, it is also going to approach either negative infinity for y or positive infinity. So for vertical asymptotes, the graph never equals that amount, wherever that vertical asymptote is. So if that x value is 2, it never crosses that vertical asymptote. Vertical asymptotes are never ever crossed because that is where the rational function is undefined. 0 is in the denominator. Got it? Yes?
An asymptote is a line where there's no...
It's an imaginary line. It's an imaginary. Yes, yes.
Where no line crosses?
Never.
Okay.
Never. But as the line approaches it from left or right, we can know, and I'm going to show you that in a minute, does the graph approach positive infinity or negative infinity? We're going to look at that in a minute, okay? So, holes, 0 in numerator and denominator. Vertical asymptotes, zeros of the denominator that are not zeros of the numerator. And they are never ever crossed. Got it? And we have one more asymptote. Horizontal asymptotes. Okay, where holes and vertical asymptotes have to do with zeros. Horizontal asymptotes have to do with the degrees of the functions in the numerator and denominator. So it's completely different. So a horizontal asymptote may look like this. So we'll just say that is at 2. And what typically happens with a graph, you can cross horizontal asymptotes. The graph can cross horizontal asymptotes. But what the horizontal asymptote tells us is as x approaches infinity, what value is y approaching? Y is going to approach wherever that horizontal asymptote is. So in this case, as x approaches positive infinity, the value of y is going to get closer and closer to 2. And maybe on this end, as x approaches negative infinity, the value of y is going to get ever so close to that horizontal asymptote value. Got it? Okay, so horizontal asymptotes, they tell us the value that y is approaching as x approaches, that's what the little arrow means, positive and negative infinity. That's what it tells us. Horizontal asymptotes. Okay? As x gets bigger and bigger and smaller and smaller and smaller, what value is y approaching? We don't look at zeros for horizontal asymptotes. I've written the rules here. Look, horizontal asymptotes. So, when the degree of the numerator is less than the degree of the denominator, all right? So the degree of the numerator here is 1. The degree of the denominator is 2. 1 is less than 2. Then there is a horizontal asymptote at y equals 0. So in this case, horizontal asymptote at y equals 0. Literally, it's the x-axis. The x-axis is your horizontal asymptote. Degree of numerator less than degree of denominator, right here. Numerator less than denominator at y equals 0. You have a horizontal asymptote at y equals 0. That's the rule. You just got to know these rules, right? Right here. Degree of the numerator is less than the degree of the denominator. Right here. Boom. Horizontal asymptotes. Look up. You're looking too far. Look. Right here. You see it? Mm-hmm. Okay. Now, when they are equal, okay? When they're equal, so the numerator is a second degree, the denominator is a second degree. Then there's a horizontal asymptote at y equals lead coefficient over lead coefficient. When they're equal, lead coefficient over lead coefficient. So, numerator less than denominator at y equals 0. Numerator equals denominator at lead coefficient over lead coefficient. Less than y equals 0. Equal lead coefficient over lead coefficient. Less than y equals 0. Equal lead coefficient over lead coefficient. There is no horizontal asymptote when the numerator degree is greater than the denominator. There's no horizontal asymptote. There is something different. It's parabolic, it's a slant asymptote, it's something else. We're not going to cover that. But it's a different type of asymptote. It is not a horizontal asymptote. And that is in here. Degree of numerator greater than denominator. There are no asymptotes. Horizontal. All right. All right, so when do we have a hole in a graph? Somebody tell me when we have a hole in the graph.
When factor completely cancels out.
When one factor completely cancels out. When do we have a vertical asymptote?
When
Zero of the denominator, but not of the numerator.
Correct. When do we have a horizontal asymptote?
You can have it when the degrees.
When the degree of the denominator is greater than the degree of the numerator.
Or if they're equal, or if the numerator's degree is greater than the denominator's.
Numerator less than denominator at y equals 0. Numerator equals denominator at y equals lead over lead. Got it? Otherwise you don't have one.
Or you do, but it's weird.
Huh?
Or you do, but it's weird.
Yeah, you do. It's not horizontal. Okay.
It's very weird without evangelism to me.
It is, isn't it? Okay. All right. Let's look at this one. What do you know about this?
The degree is 1 for both.
1 over 1. So what do you know?
There's a horizontal asymptote.
At where?
I don't know.
Y equals
y equals 1 over 3.
Oh yes.
1/3. Lead coefficient over lead coefficient. Okay? Got it? Okay, I'm going to factor this 3 out. Just so I can know, just so I can see that, okay? All right. What about holes or vertical asymptotes? Do we have any? We don't have a hole. We have no holes. Do we have a vertical asymptote?
Nope.
Yes, Allison.
Yeah, we do.
So where's there a vertical asymptote?
Wait.
Wait, what?
Wait.
Which rule is this applying?
Vertical asymptotes. What's the rule for vertical asymptotes?
No, it has zeros that the thing doesn't.
It's 3.
There is.
Oh, yes. 3 is in the denominator, but not in the numerator.
Oh,
Negative.
that's-
And x minus 2 is
What's the x-intercept?
Wait. Wait.
It is.
It should be 2 over negative.
No, 1. Constant.
2.
No, not y-intercept, x-intercept.
2. It's 1.
Guys, come on.
The x-intercept.
It's -2.
It's a 0 of the numerator. It's not a 0 of the denominator. What's the y-intercept?
2 over.
What?
Negative 2
-2/9. All right, this one. What do you know?
There is going to be.
Wait, a hole? Wait,
There is gonna be.
maybe not. Maybe.
Is there a horizontal asymptote?
Yes.
Yes.
Where's there a horizontal asymptote?
It's 1.
It's gonna
It's
be
3
1.
over 3.
It's 1.
It's 1 over 1.
Yeah. Yeah.
Okay. Is there a hole?
Yes.
Yes.
No.
Who said that?
No.
It says,
Because they're both equal, so there is x-intercept in the denominator and the numerator that are equal. So there's not. What I mean is, there's not an x-intercept in the denominator that's not in the numerator.
Look, holes. 0 of the denominator and the numerator. As long as they can be canceled.
There is a hole, right?
There's a hole.
I told you guys.
Yes.
Oh, I meant yes.
There's a hole at x equals 3.
I thought there was just one. Okay.
Right? Is there a vertical asymptote? No, because they can be canceled.
I meant for vertical asymptote.
They can be canceled. Is there an x-intercept? No. Is there a y-intercept? 1. All right. Now, let's look at this one.
Oh boy.
No, there's
Is
not.
there a horizontal asymptote?
No.
Why? Why?
It's the multiplicity is higher in the
The numerator is greater than the denominator.
This is a squared term. This is a first degree. There's going to be a different kind of asymptote, but no horizontal asymptote. Is there a hole in the graph?
No.
No. Because it doesn't cancel out.
Yes. No.
Do they all cancel out of the denominator? Out of the denominator completely cancels out.
Yes.
So there's a hole at x
Wait.
equals 3.
It says
Except when the multiplicity
Except when the multiplicity of the what?
it doesn't say.
Denominator.
is higher than the numerator.
Yeah, except when the multiplicity of a factor is higher in the denominator than it is in the numerator. Here, the multiplicity is higher in the numerator than the denominator. So that's a hole. Got it? This one is not a hole.
It does not completely cancel out.
It's a what? This is not a hole. This is a
Horizontal asymptote.
vertical asymptote when you can't cancel out the denominator. Vertical asymptote. You see that? When I can cancel the denominator, there's going to be a hole in the graph. When I cannot cancel out all of the denominator, there's a vertical asymptote.
But there's also a horizontal asymptote. No, zero.
X equals 3. That's 1 over x squared, right? So the numerator is less than the denominator, so there's a horizontal asymptote at y equals 0. Okay. Let's walk through the examples. All right. Starting on example 3 on page 281. All right. We have x plus 1 over 2x minus 4. All right. Do we have an x-intercept?
Yes.
At x equals what?
-1.
So negative 1. Do we have a y-intercept?
Yes.
Negative 1/4. Do we have a hole in the graph? Okay, that'd be 2 times x minus 2. I just factor the denominator always and the numerator. So no hole. Do I have a vertical asymptote?
Yes.
What is a vertical asymptote at?
1.
What's the definition? When do I have a vertical asymptote?
And the 0 the denominator, but not the numerator.
Okay, so vertical asymptote at x equals 2. What about a horizontal asymptote?
Yes.
1/2.
At 0.
No. Numerator equals denominator at y equals 0. You see that? Oops, I almost dropped my.
Lead coefficient.
No, numerator less than denominator. Y equals 0. They're the same, so it's lead coefficient over lead coefficient. Y is 1/2. Look, y'all just did everything with that. All right, go over to example 4. Okay. Do we have an even number here? We don't have an even number here. Okay. I'm going to work this one, and we're going to talk about end behavior.
Okay.
But I also want to work B. Okay. So we're not going to work A.
Where
But
are we? Where are we? Oh,
example 4. But for A, I'm going to keep using this one. We are going to look at B. Because B is a little different. All right? So for end behavior. All right. Remember I said something happens at 2, right? Because there's this vertical asymptote. So we're going to answer the question as x approaches 2 from the left. Is the graph going to positive infinity for y or negative infinity for y? Okay? So this is what we're going to look at. It's called the big little concept. Okay? All right. 1 over a very big number. What does it equal?
Very small.
Very small. It equals very small number. Okay? So as the denominator gets bigger, this is going to get smaller. And then if we do 1 over a very small number like 0.001, then what's the result? It's a very big number. So this is the big little. They don't call it small, they call it little. Big little or little big concept. That's the way it is in almost all the textbooks. And it's saying when the denominator is a big number, then the result is going to be a very small number. When the denominator is a very small number, then the result is going to be a big number. So this is going to tell us, are we going to positive infinity or are we getting smaller and smaller and smaller? All right? So what happens as x approaches from the left-hand side? All right, so we're going to look. I'm going to go over here. We're going to look at the numerator and the denominator, all right? All right, so y'all, this is going to be like a calculus sort of concept, all right? This big little thing is very similar to calculus, all right? As we approach from the left, we get ever so close to 2. So I'm talking about 1.9. I'm talking about 1.99. I'm talking about 1.999. So close. What happens to y? Got it? That's what I'm talking about. So we're going to look from the left. As x approaches from the left. That's how you write it. It'll be negative, all right? As x approaches from that asymptote from the left. All right, so we're going to plug in numbers for x. 1.9, 1.99, 1.999. All right? So we're just going to say positive number and we're going to say big or little. All right? So in the numerator, if I put 1.9, it's 2.9, right? If I put 1.9 in here, does it equal 4?
It gets really.
It's a small negative number, don't you agree?
Yeah.
It's a very small negative number. If I put 1.9. It's going to be a small negative number. Because 2 times 2 would be 4, that'd be 0. So 1.9 times 2 is going to be smaller than 4. It's going to be very small number. Okay? Negative number. And this is going to keep getting smaller, right? This is going to keep getting smaller. A smaller negative number. A smaller, littler, smaller. So as the denominator gets to be a smaller negative number, where's y going? It's a positive over a negative, so y is going to be approaching negative infinity. It's going to be a big negative number. It's going to be a big negative number. Got it? So from the left, y here, y is going to be approaching a big negative number. Got it? Because that big little concept. All right, from the right, so as x approaches from the right, now we're going to just go just above 2. So we're going to look at 2.001, 2.01, 2.1. All right, so when I put in 2.01, we still have a positive number, right? 3.001. Now, 2.001 times 2 is just going to be just a little bit over 4. Do you agree? 2 times 2.001 is just going to be a little bit over 4, right? So when I subtract 4, it's going to be a very small positive number. So it's going to be a very small positive number. So, it just keeps getting a little less small and a little less small. As I go from here to here, that number gets smaller and smaller. From here to here in the denominator. So what from the right is y approaching? It's positive over positive, but the denominator is small. Positive infinity. So it's going to be going up. So we can tell what our behavior is going to be as it approaches those asymptotes with that big little concept. Now, this horizontal asymptote whereas the big little concept tells me what happens around that vertical asymptote. Got it? The big little concept tells me what happens around that vertical asymptote. My horizontal asymptote, I'm going to back up and say one more thing. The big little concept tells me what value y is approaching as x approaches that vertical asymptote. Okay, I'll say it again. The big little concept tells me what is y approaching as the x value approaches that vertical asymptote. And it's either positive infinity or negative infinity based on the small, big, little concept, okay? The horizontal asymptote tells me as x is approaching negative and positive infinity, what is y approaching? And it's going to approach 1/2. Okay, I'm going to say this again. All right, vertical asymptotes tell me is y approaching positive or negative infinity as x gets closer to that vertical asymptote. Sam, hang with me. Okay, the horizontal asymptote tells me y is approaching that horizontal number as x is approaching negative infinity, as the x is approaching positive infinity. Okay? All right, so we're going to look at example B. Well, maybe let's jump. Let's jump a little bit in the text to I don't want to do 8. This was the last example I was doing. Okay, great. All right, let's do B of example 4. All right. So, x-intercept, y-intercept, holes, vertical asymptotes, horizontal asymptotes. Okay. Are there any x-intercepts? Come on.
No.
There are. What is it?
Would it be 0?
0. Yes. Okay. Is there a y-intercept? At
0.
0. 0 over -4. All right. Is there a hole in the graph?
Yes.
What are holes? Zeros of the numerator that are zeros of the denominator. No holes. Is there a vertical asymptote? Are there vertical asymptotes?
Yes.
Yes.
How many?
How do you tell how many there are?
Well, what is by definition a vertical asymptote? Zeros of the denominator that are not zeros of the numerator. So if I have 5 zeros in the denominator, I have 5 vertical asymptotes.
So 2 is
So what? No.
No, 2. Because it's x.
Is that it?
It's x plus 2. It's x minus 2.
2 and negative 2.
2 and -2. Plus and minus 2.
Wait, why is it plus and minus?
Because -2 squared is 4. Positive 2 squared is 4.
That's not
Okay? Horizontal asymptote.
Yes.
Yes, there is.
At y equals
0.
0. Numerator less than denominator. All right. And we can figure out as x approaches infinity, it's going to approach 0. It's going to be approaching the y-axis. Something happens at -2, something happens at 2. Maybe it goes negative infinity or positive infinity, but we would use the big little concept to figure out. We could use the big little concept. Does it go down, up, and then down again? That's typically how it looks. Or does it go up, down, and up again? But you would do the big little concept.